All right, so we just looked at a couple of warm-up exercises that were laying the foundation for what we're going to come to call the integral test. And an offshoot of the integral test is a P-series test. As a matter of fact, the P-series is just a special case, very easy to apply, probably even easier than the geometric series test, just saying. Okay, so let's take a look at the integral test, shall we? So first of all, I want you to understand that all of the calculus that we've done, like when we're doing derivatives, when we're doing integrals, we needed continuous functions, right? A series, a sequence, and a series, these are not continuous things. They're discrete. You just have a set of points and that's it, right? So what we do is we take those dots and we come up with a function that models those dots. Let me come over here to like the slide just for a second here. So it's like this. Like I wouldn't actually have this particular function right here. Instead, I would have dots on that function. Right, so I would have just a series of dots. And this function goes through all of those series of dots, and we're going to do our calculus on the function, not on the dots. All right, so that's what we do. That's the major technique here. All right, back to the slideshow. So if f, this is the function that we're using to represent our series, basically. If f is positive, continuous, and decreasing for x greater than or equal to 1, and we're letting this function equal the terms of our sequence, this a sub n, that's what that means, then a couple things here. This is the integral. It's the improper integral from 1 to infinity of f of x dx and the infinite sum. The sum from n equals 1 to infinity of a sub n, that's the terms of our sequence. That's actually the series, right? Both of these things, they do the same thing. They both either converge or they diverge. So I take a look at the integral. Does that thing converge? If it converges, so does this one. If this thing diverges, if the area shoots off to infinity, then this must shoot off to infinity as well. Because remember, what actually was happening is that we were looking at a set of dots on that graph, and if that area goes off to infinity, we're saying that this thing does too. Now, there is a little footnote here. When I figure out that this integral actually converges, and I'm able to conclude that this series converges, that doesn't mean that they converge to the same thing. And we'll see why that is the case here in a little bit, right? This thing converges, so does that. Maybe this converges to 1. There's no indication that this also converges to 1. So let's look at some pictures, help us understand what the heck's going on. Why does this thing actually work? Now, in the wording of the test, it does say that our function needs to be decreasing for x is greater than or equal to 1. Well, we can get around that particular thing as long as our function is ultimately decreasing. The test will still hold. Like, for example, it might go up a little bit, and then maybe it doesn't start decreasing until n is equal to or x is equal to 2 or 3. Well, then it'll still be okay, and I can still apply the test after that particular point. Okay, so when we're finding a definite integral, we're basically finding the area underneath that curve, right? So if I have the curve 1 over x squared, we saw that the area converged to 1. So it was a convergent area. When I'm looking at the sequence, however, the sequence, it's just a set of dots that are on that. And I can represent that those set of dots with a Riemann sum, as you can see here. So for the first one, our first term was supposed to be, if I plug in 1 into that function, I would get 1. It's the same thing as the area that's right here, a 1 by 1. This right here is a right Riemann sum, right? Because we're using the right endpoints. Okay, if I were to stick in 2 into that function, 2 squared is 4, I'd have 1/4. This is a 1 by 1/4, so this rectangle represents that 1/4. Right? And then if I were to stick in 3 squared is 9, this is 1/9. This is a 1 by 1/9 rectangle, the area of that represents that term, and then so on. And you can see that every single one of those rectangles fits very, very comfortably underneath that curve. And if the area underneath this curve, which we found by the improper integral, if it converges and our series is smaller than that convergent series, that convergent area, then it must also converge, right? So that's the basic premise behind this. We're smaller than a convergent area, therefore our series must also converge. If you are smaller than a divergent series, you know nothing. But if you're smaller than a convergent series, you do know that it has to also converge. Okay, so let's look at the divergent side. This one is looking at the function 1 over the square root of x. We did in our warm-up exercise 1 over x. Okay, but it's going to work the same way. 1 over the square root of x, it would also diverge. Okay, so in order to use that same exact technique, you have to be bigger. You have to be bigger than a divergent. If you're smaller than a divergent, you have no idea what's going on. You have to be bigger than a divergent. So for this particular case, we're going to use a left Riemann sum. And the reason why is if I were to stick in 1, I would get 1 over the square root of 1, which is 1. So the first little area here to represent that first term needs to be a 1 by 1, and the area is 1. If I were to stick in 2, I'd have 1 over the square root of 2. So this length down at the bottom, the change in x is 1, and then the height here is the square root, 1 over the square root of 2, and then so on. And you can see for this particular sum, it's a little bit on the outside, which means that that sum is actually bigger than the area. It overestimates the area. We're bigger than a divergent series, therefore it has to diverge. Okay, so I know what you're probably thinking. Well, why did we use a left Riemann sum on this one to show that it diverges? Why didn't we do the same thing on the previous one? Because remember, as far as divergent goes, if you're smaller than divergent and you don't know anything, it could still diverge or it could converge. In order to show the divergence, it has to be bigger than something you already know diverges. So the same thing goes back over here on this one. We could use, maybe even draw pictures here. Come back over here to Notability. If it loads, it's working. To this set of pictures here. Let me use a different color. Absolutely, we could have used a left Riemann sum on this one. So here's the first one, right? Boop. And then the second one would have been, come on, really? Do not disturb, does nothing. Here, and absolutely, we would have been on the outside. But the problem with this is that all it showed was that you're greater than a convergent series. What does that mean? It doesn't mean anything. Just because one of them converges, you're a little bit bigger than that. It could still converge, or maybe it diverges. You don't know enough information. So this was the best way, the original way, was the best way to approach this. We knew that 1 over x squared converges. So can we arrange our particular series so that it's smaller than that, right? We can still arrange this, the sequence that is represented by this particular function by something that's smaller than that. But if you're smaller than a divergent series, like for example, we could have gone here, we could have gone here, we could have gone here. It's smaller than a divergent series, but again, you wouldn't know anything. It doesn't tell you anything. So we had to force this one into being something that was greater than a divergent series. Okay, so let's see if we can apply it to our first little series here. Determine whether the sum from n equals 1 to infinity of n over n squared plus 1 converges or diverges. So what we're going to do, of course, is use the integral test. In order to use the integral test, we need to make sure that we check all of the conditions. Make sure that conditions are met, and then we can perform the integral. Okay, so then, on example 1, our series was sum from n equals 1 to infinity. I think it was n over n squared plus 1. I'm going to go with yes. So what we want to do is consider a function. This is a set of dots. We want to consider a function that represents all of those dots and then actually fills in all the gaps too. So that will just simply be, you switch the n's to x's. That's all you do. Right? This is discrete. This is hopefully continuous. That's what we have to make sure that we point out. All right. So let's meet our conditions. The first one is it positive? It doesn't need to be positive everywhere. It just needs to be positive as long as x is greater than or equal to 1. So our function, f of x, is equal to x over x squared plus 1. Just take it in parts. Look at the bottom down there. It's x squared, which is positive, plus 1 more is also positive. So no matter what, this bottom is always positive. Okay? The top is x. X can be either positive or negative, but as long as x is greater than 0, if x is greater than 0, this whole entire thing is going to be positive. All right, now remember that all I needed to show it was greater than 0 for x is greater than or equal to 1. And that's pretty much all you have to show, right? You just have to point it out. You make that kind of judgment, oh, these things are positive terms for x greater than or equal to 1. All right, we're in business. Our first condition is met. The second condition, is it continuous? Well, to answer that question, just what kind of function is this? So f of x it's rational. And rational functions are continuous on their domains. Really? Really? What's continuous on its domain, not their domain? I got distracted by the emails. All right, and so let's take a look at what that domain is. So it would only not be continuous if it had some vertical asymptotes. But this thing we said down here at the bottom was always positive, right? There's no value of x that you can stick in here to make this equal to 0. It's always positive. So that means it's actually continuous everywhere. So f of x is continuous everywhere. Doesn't have any asymptotes. If it's continuous everywhere, it must also be continuous on x is greater than or equal to 1. So, boom. That one is also checked off. Continuity, yes. Positivity, yes. And then our last condition to check is it decreasing? So, way you count is 1, 2, 3. Okay, yeah, I got it. Decreasing. So to check decreasing, of course, we take its derivative. And we got a quotient. We'll have to use the quotient rule. F prime of x is equal to derivative of the top is 1 times the bottom, x squared plus 1, minus the top times the derivative of the bottom, which should be 2x, over the bottom squared, x squared plus 1 squared. And now let's simplify here, because that second part here is a negative 2x squared, right? And then whenever I combine this up, I get 1 minus, let's see, combining like terms, 1 minus x squared over x squared plus 1 squared. All right, so again, we want to take it in parts. This part here is always positive because it's being squared. So it only matters about the top. So look at the top there. So on the top part, we have 1 minus x squared. Well, it will be positive as long as this x squared is smaller. Well, let's see, is this right? As long as, no, we don't need it to be positive. We actually need it to be negative, right? So it's going to be positive if it was smaller than 1, and it will be negative if it's greater than 1. So, no, I want green here, so negative for x is greater than 1, right? If it was equal to 1, it'd be 0, but if it's greater than 1, then that x squared's bigger, and so it'll take on that sign. So we're going to say that this thing is less than 0 for x is greater than 1. What's that mean? If your derivative is negative, that means that your function must be decreasing, right? Since f prime of x is less than 0 for x is greater than 1, we can conclude f of x is decreasing. So increasing or decreasing happens on closed intervals. So on x is greater than or equal to 1. Bam! All right, so we have met the third and final criteria. Our function was positive, check. It was continuous, check. It was also decreasing, check. So then I get to actually do the integral test. Hooray for me. So to do the integral test, we're going to consider the definite integral from 1 to infinity of x over x squared plus 1 dx. All right? Pay attention to the notation. Use it appropriately. We have an improper integral, so fix it. Limit as b goes to infinity. Definite integral from 1 to b, x over x squared plus 1. All right, how are we going to integrate this one? This one's pretty easy. Let's just use substitution. Where our u should be x squared plus 1, meaning our du is equal to 2x dx. I don't have a 2. Let's fix that. Put a 2 there. Put a 1/2 in the front to compensate. And notice that what we have here is a du over u. Antiderivative of du over u will be a natural log. All right, so this is equal to the limit as, I think that's a b, goes to infinity, of 1/2 the natural log of the absolute value of x squared plus 1. And then we'll evaluate that from 1 to b, of course. Limit b goes to infinity. That looks like trash. Let me fix that. Of 1/2 the natural log. B is always a positive number. It doesn't even matter. I can get rid of the absolute value here. So b squared plus 1, boop, boop, minus 1/2 the natural log of, I stick in 1. 1 squared is 1, plus 1 more is 2. Okay, not that it really matters, as you'll see. If I were to plug in my infinity, that's infinity squared plus 1 is still like super big. We take the natural log of something super big. This is going to shoot off to infinity, which means our whole improper integral diverges. Okay, if it diverges, that means our series must also diverge. So this is the way I make my conclusion. Okay, since I have to make sure that in my conclusion I point out all of those conditions that worked and then draw the proper conclusion by the integral test. So since f of x equaling x over x squared plus 1 is positive, come on, positive, continuous, and decreasing for x is greater than or equal to 1. Okay, so those were the conditions. And the improper integral from 1 to infinity of x over x squared plus 1 dx diverges. Then our infinite sum. So I write that sum as from n equals 1 to infinity of n over n squared plus 1 also diverges by the integral test. Boom, boom. That gets a highlight, and apparently it gets a highlight in green. Okay, so again, recap there. I said that our function was positive, continuous, and decreasing. It met the conditions for the integral test. The actual improper integral diverged. So then the integral test is telling me that my series, my infinite series, must also diverge. All right, so here's all of that stuff kind of animated for us. I'm looking at my function. I consider a function that replaces my series here. Is it positive? Check. Is it continuous? Check, yes. Is it decreasing? How do I check decreasing? I check its derivative. All right, and its derivative is less than 0 for x is greater than 1, so it's decreasing, check. So then I take the improper integral of our function from 1 to infinity. We just saw that that was infinitely big. It diverged. Insert calculus here. We already did the insertion, right? And so we can conclude by the integral test that our series also, in fact, diverges. All right. So when we come back, we'll, I don't know, maybe wrap this up just a little bit and then take a look at another example or two.